Hello class. Today we are going to talk about the third thermodynamic parameter, Gibbs free energy. This is the asynchronous video on Friday. Happy July. And this delta G, it's also called chemical potential energy, and it's a thermodynamic state function related to enthalpy and entropy. State function means that it's a parameter or a quantity that is not dependent on the path you take. So for instance, if you go up a hill, right, the height at the top minus the height that you start out with, which is the delta height, well, that height is going to be a set number regardless of the path you take. So the height of a hill is a state function, but whereas the distance you travel going from the bottom to the top, well, that distance can be very short if you take a straight line to the top, or if you take a windy path. So that's how I like to think about state functions. When climbing up a hill, the final height and the initial height, the delta height, is a state function, but the distance traveled is not a state function because it is dependent on the pathway. Anyway, if you know the final state or the final free energy of a system and the initial free energy of a system, all you have to do is take final minus initial to get delta G. Same thing with delta H, delta S. Those are all state functions. But what's more important for us, that was a little bit of an aside, is that we understand and apply this equation, delta G equals delta H minus, sometimes people, myself, get that sign wrong, delta H minus T delta S. Delta H minus T delta S. And the thing about these variables, we talked about enthalpy and entropy already. Just be careful about the units. We'll have a problem in just a bit, because you may need to convert the entropy into kilojoules per mole dot K, because you want to match those units, the energy unit, with the enthalpy and entropy. Okay, or vice versa. You could convert delta G and delta H into joules per mole. Okay, so please make that correction. Great, like the first 2 minutes and there's already an error. Make that correction, please. Another thing about Gibbs free energy, where does this word free come from? It's often energy released from a chemical reaction. That energy is used to do work, like an expanded gas to move the piston, which moves the car. So that change in this type of energy of a chemical reaction, represents the maximum amount of energy available or free to do work. So that energy is, again, available or free to do work. Not really an important definition for you to know. It just tells you where people came up with the term free energy. These days, most chemists are just saying gives energy, because free is a little bit misleading for some systems. Okay, negative and positive delta G. Whether you take delta G or delta G of a specific reaction, if it's negative, that's important. The process or the reaction is spontaneous. Okay, so you're looking for negative delta G's if you want a reaction to go forward. Now, the thing is, we don't use the terms endothermic or exothermic. For delta G, we use the term exergonic if it's negative, and here it says positive. We use endergonic instead of exo and exothermic and endothermic. So, as you know, exothermic and endothermic refer to enthalpy, delta H. Delta G has its own two terms. And again, if it's positive, then it's reaction is non-spontaneous. And if you have a reaction that is spontaneous in the forward direction, if you go in the reverse direction, it has to be the opposite. It has to be non-spontaneous. But what if it's in the middle? What if it's neither negative or positive and it's zero? That means the system is at equilibrium. We'll talk more about equilibrium in the next couple of classes. But what it essentially says is that the forward direction and the reverse direction are happening at the same rate. They have the same rate of reaction. So it appears that nothing's happening, right? You don't have any changes in the quantity of reactants and products once the system is at equilibrium and delta G is 0. Now you may want to review spontaneity and how to determine that qualitatively. But now, since we have these two rules, we can now determine spontaneity quantitatively by calculating for delta G. Let's take a look at a first problem, and we are going to use that equation. Let's read it first, actually. One of the initial steps in the formation of acid rain is the following oxidation of sulfur dioxide. If what? What is delta G naught for the reaction? Holy smokes. And we are given delta H and delta S. Alright. The second part is the delta H and delta S values are at 25 degrees Celsius. So is this reaction spontaneous or non-spontaneous at 25 degrees Celsius? Get rid of that if. You notice that delta G is, there's a temperature term, and the value and the sign of delta G will a lot of times be determined by what this temperature is, because many processes are actually temperature dependent. Some are not, right? Some are spontaneous at all temperatures, and we'll see examples of that. Let's take a look at this example specifically. I like to write out my equation that I think I'm going to plan to use. Okay, and then when studying, I want to mark or know what the units typically are. Temperature has to be in Kelvin. Okay. Remember how I warned you that you may have to convert that unit so they match? Let's do that. Let's convert the delta S into kilojoule per mole dot K. And a joule is smaller than a kilojoule, so there are less kilojoules. The number will be smaller. So we're going to move the decimal point 3 times to the left. That will represent kilojoules per mole dot K. So this equals negative 188 0 negative 0.188 kilojoules per mole dot K. You know that K is going to disappear when we multiply by temperature. The other thing is T has to be in Kelvin, so we're going to convert that Celsius. That's 25 plus 273.15, so 298.15 K. I think this is going to work. They just want us to calculate for delta G. So delta G naught reaction equals delta H is negative 197.8. I normally don't put the units when I start writing out when I start plugging in numbers. I don't want it to be too cluttered, but I'm very confident that we'll get the right units. Minus 298.15 times negative 0.188, and just double check the K will cancel out when you multiply these two, and then kilojoules per mole minus kilojoules per mole will give us the answer in kilojoules per mole. Find your calculator. What am I going to do first? I'm going to do this first. So 298.15 times negative 0.188. Okay, that's an answer. And I'm going to take that number minus the answer. So negative 197.8 minus the answer. What do we predict? I don't know what to predict. That's a minus of a minus, that's positive. So it would be less negative. So negative 141.7478 equals negative 141.7478. Don't go too crazy with significant figures. We're going to limit ourselves to 2 significant figures because of this. No, because we use that in the equation. So we're going to convert this to, or round it to 140, and that goes to, well, that's 0, right? We don't want that to be significant. So that's 2 significant figures. For my class, if you put 141, heck, even if you put 141.7, I'll probably still count it correct. I just don't want a long string of digits. This one's 7 digits. That's, I think, too much. Okay. Units. You gotta put units or else there'll be a point deduction, and circle your answer. Is this reaction spontaneous or non-spontaneous? This is spontaneous at 25 degrees C. Now the thing is, okay, so those are the 2 answers. Is it going to be spontaneous at all temperatures? I think if this temperature goes very, very high, we're going to minus a bigger negative number, so we're going to add a number. And maybe at some point we're going to add a number that converts this term to a positive number. Right? We'll add a large positive term, and it will get rid of this negative sign. So in this case, I'm not asking this. We'll do this in the next page. It is temperature dependent, and the higher the temperature, it will turn non-spontaneous. We'll do that thought puzzle on the next page when we talk about signs. Okay. Double check my answer. If it's incorrect, go ahead and let me know. Let's look at part B. Revisit spontaneity and delta H and delta S. From class 2, we looked at the process of ice melting. At negative 5 degrees, that solid will melt. Ice melting, no. At 5 degrees is non-spontaneous. Ice melting at negative 5 degrees. Ice does not melt spontaneously when you're below the freezing point. So that's non-spontaneous. But at 10 degrees, at above melting point, ice spontaneously melts. Okay, so please make that change. The sign of delta G appears to be temperature dependent because depending on the temperature, we can make the process of ice melting either non-spontaneous or spontaneous. So let's take a look at that process again. Going from, ice to liquid water, solid to liquid. What is the delta H? Could you fill in these 3 blanks, actually? You could pause the video, fill in those 3 blanks, and you could compare your answer to mine in just a bit. Okay, when solid things melt, you're inputting heat, energy, right? So that sign is positive. Now, when you're comparing solid to liquid, who has more disorder? It's the liquid state that is more disordered. So we went from a low entropy, less disorder, to more disorder. So that is a positive delta S. Entropy is a measure of disorder, chaos. The delta G sign, if you're not giving any temperature, right, this is a variable. It depends on T. And we know that because from this fact, we know that ice melting can either be non-spontaneous or spontaneous depending on temperature. So the delta G sign is dependent on temperature. Now, we could also predict, well, when would it be spontaneous? Let's say it's spontaneous if, let's not even look at the parameters. What does your instinct tell you? Melting is spontaneous when the temperature is high or when the temperature is low? Melting is likely to be spontaneous when the temperature is high. Spontaneous if you have a high temperature. And does that work? Well, your equation, I'll put it here because we already need it. Delta G equals delta H minus T delta S. If your enthalpy is positive and your entropy is also positive, you notice that the bigger the temperature, the more negative term this becomes, and the more likely that delta G will be negative. Okay, so that correlates, that a high T will make this delta G negative. In this case, a high T makes delta G negative. Okay. So let's play that game for question number 2. Fill in the delta G column with plus, minus, or negative when T is large, or negative when T is small. So I'm really asking you here, what does the temperature have to be spontaneous? To be spontaneous. Okay. Let's do this in order. Delta H is negative. Delta S is negative. Can we look at let's look at the equation. So if delta H is negative, that's good for delta G to be negative. But delta S is negative and we're minusing a negative number. So we don't want this term to be big, or else this would be a bigger positive term because a negative times a negative. So we don't want this term very big. T should be small. Then delta G is negative if T is low enough, but we'll just say T is small. Negative when T is small. Okay. What about negative and positive? Well, if delta H is negative, well, let me pause right here because I know some of you have done this before. Why don't you pause the video and fill in the rest of this table for delta G, and then you can compare your answer to mine. Delta H is negative, great. So far delta G is negative if we only had delta H. Delta S is positive, but we're minusing a positive number, so we're getting even more negative. This delta G will be negative, and I'm going to even put always, or we'll say at all T, at all temperatures. Positive and positive. We have that situation here. So you want delta T to be high, to make us minus a larger number. So if negative if t is high or large. Okay. And we concluded that already. Negative negative. No. This should be positive. I'm going to be making a lot of corrections, but whatever the handout is right now, which the one I'm working on, I'm going to keep that on Canvas. Please be sure to make all the corrections that I'm spotting. We haven't done the positive negative situation yet, and so that delta H is positive. We're minusing a negative delta S, so that will always be positive. We're adding a positive. That means that delta G is always delta G is always positive at all temperatures. Okay. Now, if you want, you could put positive at high temperatures, positive at low temperatures. I don't suggest you trying to memorize this table. Okay. Try to think it through on a case-by-case basis, and see if it makes sense. Right? It makes sense that here it will be spontaneous if temperature's higher because we're talking about melting. Okay. Next, a little bit of review and applying this to delta G, because we know that this delta H of the reaction, we can get it from the enthalpy of formations of the products minus the reactants. Now this N is the coefficient, so I don't have a equation here. Right, if we're going to use this equation, you need the formation of the product, and then you multiply it by 2. Minus the heats of formation for these molecules multiplied by their coefficient added together. Okay. Remember about oxygen gas, the delta H formation? That's the natural state. So this is 0. Okay. Well, just the way we could solve for delta H of the reaction using the heats of formation, we could solve the delta G reaction using the delta G of formations. Delta G of formations. I said that right. Okay. So there are now 2 ways to calculate delta G if you're given delta H and delta S, or if you're given a table or a list of free energy formations of the products and reactants. We could also do this for entropy. We didn't formally go over this, but hopefully you drew this conclusion. If you have the entropy of the products, again, don't forget to multiply it by the coefficients, minus the entropy of formation of the reactants, you could get the delta S. What do you notice about these 3 equations? There's something odd. The entropy, the tables that you're going to get for entropy do not report delta S. Entropy can actually be measured as an absolute value, and then we take the final minus initial. So I'm going to leave it at that, but take a look at a standard thermodynamic quantities for selected substances table. These are your thermodynamic parameters, and look at the units. I'm going to write here, notice the units. Okay, kilojoules per mole, and we're back to joules per mole .K for entropy. The other thing that that we need to correct, it's not really entropy of formation. It's literally the entropy of the molecule. So we're going to get rid of this. This entropy formation is actually a delta G because it's the reaction is making a mole of a compound from its elements at standard state. So there's a reaction and there's a product side and a reactant side when we think about formation. Okay. Not a big deal. I just don't want you to get hung up in the fact that you don't report delta S's for substances. You report literally its entropy. The other thing is entropy is not zero ever, because theoretically entropy of 0 means that it's a perfect crystal at 0 degrees Kelvin. Okay, and we all know that for these tables, standard means 25 degrees C. So that will never be 0. This is never 0. But what is 0? When you have an element in the standard state, we already talked about the heat of formation is 0, but also its free energy. So take a look at that. I'll circle it. Those are zeros, because this is an element in its standard state. Is there anything else? You have water at different states, liquid and gas. So those values also are different from each other. Okie dokie. Last page. Let's go to page 3. So we're going back to a little bit of enthalpy, but we could also get free energy of vaporization and free energy of fusion. We could get the delta G's as well. But I want to go over this concept for enthalpy. The heat of vaporization, the delta H VAP, or VAP, is the amount of heat required to vaporize 1 mole of liquid to a gas. So your equation is this. You could pretend this is water, methanol, acetone, anything liquid that can evaporate. So the delta H for this reaction, where you convert from liquid to gas, a phase change, that heat of reaction, we call it the heat of vaporization. So those are equal. Okay. Now if you take the reverse, if you go from gas to liquid, you take that number, like typically you look up these numbers of heat of vaporization, heat of fusion, but if you're going in the reverse direction, where you take gas and what? You lose energy to become liquid, you take this number and you make it negative. So this heat of vaporization, because it's heat required, you should always see it as positive. Okay? But if you're going from gas to liquid, you have to make it negative. Okay? Just take that value and make it negative. How about heat of fusion? Heat of fusion is a little bit odd, because it's not you're fusing things together. The definition is the heat required to melt a 1 mole of solid to liquid. So again, the heat of fusions, when they're reported on tables, they should be positive, because in these two cases, you are adding energy. Here, fusion, you are adding energy, solid to liquid. And I have that, good, solid to liquid. Now if you reverse it, your value for the delta H reaction will be the negative delta H of fusion. Why don't we put down, these, whether these processes are endothermic or exothermic. So just to verify the signs. When you go from liquid to gas, okay, you're adding heat. So that is endothermic. And we know that endothermic reactions have a delta H that's positive. Right? Gas to liquid, losing energy or losing heat. Exothermic. This one, endothermic. Solid to liquid, you're adding heat. And exothermic. Okay, you could pause the video and make sure this makes sense to you, but I know for a lot of you this is pretty automatic. Okay. Now, just like we have delta H vape delta H fusion. We could have the delta S of that process, and we could have the delta G. You know what this is called? When you go from gas to liquid, this is condensation. Right, and here we have evaporation. So the thing is, we're vaporizing and there's a delta H vape. We don't call it delta H condensation. We just take the negative of the vaporization. Same thing here. This is melting. The opposite of melting, freezing. Freezing. Okay, and there is no heat of freezing. We just take the negative of the heat of fusion. Okay. Last problem. Last page, last problem. Alright, we're going to do this on the fly. The molar heat of fusion and vaporization of mercury are 23.4 and 59.0 kilojoules per mole respectively. Calculate the molar entropy. Calculate the molar entropy. Oh my goodness. For the solid, liquid, and liquid vapor transitions for mercury. So that is the fusion, liquid to vapor. That is vaporization. At 1 atmosphere pressure, mercury melts at this temperature and boils at this temperature. So the thing is, there's a lot going on here. When there's a lot of information, I like to restate the information so it's visually familiar. For instance, delta H fusion is the molar heat of fusion, and that equals 23.4 kilojoules per mole. Okay, so that's one thing. Restate the data in a fashion that is a little more familiar, and then maybe possibly jot down any equations that you think you may need. The problem is, it's not a problem. The thing is, we have delta H's. They're asking for delta S's. And we have temperature. Okay. Possibly we're using this equation. Now we're not given delta G. But for me, if I jot something down on paper, I have a better chance at, seeing where the twist is. What piece of information could I get maybe indirectly? Because we're not given delta G's here. But we are looking for, right? We're looking for delta S's. If you use those two tips, for me at least, I have a better chance at solving a word problem. Okay? So why don't you do those tricks? If it doesn't, maybe it occurs to you very naturally what to do here, but for me it's not straightforward until I start organizing my givens and variables. Okay, why don't you pause the video and give it a go. The least you can do is, if you're stuck, is try to use some of my tips. That is the delta H of vaporization, and great. They're both positive. We're looking for delta S. Okay. We have T's. We have T of the melting. That equals, now because I have this equation written out, it reminded me that temperature has to be in Kelvin. So let's do the melting point first. Negative 38.9 plus 273.15, 234.25. The T of boiling, the boiling point, oh, it's pretty high. 357 plus 273.15, 630.15. There is a question like this, I believe, on the practice problem, so See if you could use the same strategy. So here's the deal. Remember when we talked about melting point of ice and it was temperature dependent, and at 5 degrees we see that delta G is positive because it's non-spontaneous. 10 degrees it's negative, but at some point, at some temperature, it crossed over from positive to negative. At some point, delta G is neither negative or positive, it is 0. And you know what that point is? That point is the melting point. The melting point is the temperature at which delta G is 0 for this process. So indirectly, we know we could get delta G because we could set delta G to 0. For instance, for let's say vaporization, if we have delta G equals 0 when T is at the boiling point, right? That is when it crosses over from spontaneous to non-spontaneous. So I want to do this kind of carefully. I wish they had talked about vaporization first, but let's use the heat of fusion. So heat of fusion, right, is the solid to liquid transition. So I'm color coding also. Everything in pink is what I'm going to consider first. And we need, is that right? Yeah, solid to liquid fusion. So we need the melting point. The melting point is the temperature at which the solid and liquid are at equilibrium. Whew. At melting point, delta G equals 0, and I need the delta H 23.4 minus, I should have circled this one here, minus the melting point, 234.25. So just give me 1 second. If I want to just super double check about the sign of this enthalpy. Because if I am really looking from solid to liquid, I gotta double check that delta H is, yes, in the positive sign. So I'm using this. Literally, I'm just taking the heat of fusion. I think that makes sense, actually. Because what I'm really looking at is delta G of fusion equals delta H of fusion minus T delta S of fusion. And literally, that is what they want, the molar entropy for fusion. Okay. Delta S. Oh, we're solving for that. Delta S. Fusion. Okay. What would I do? I would bring over this term first, so that's negative 23.4. And then I'm going to, cover that up. I'm going to divide by negative 234. Yeah, 234.25. Is that true? 234. Where did this number come from? Oh, it came from here. 234.25, the temperature. Equals. Alright. Delta S of fusion equals, you see that? 0. Let's use 3 significant figures. 0. Oh boy. Well, that turns, okay, good. 999. I thought I was going to have to round to 0.1. So that's 3 significant figures. That rounds up. That rounds up to 9. Units. See, we use kilojoules, so this has to be kilojoules per mole, but the entropy, as you know, has a per K term also. See, from your thermodynamic parameters table. Circle your answer. Okay. You want to do the one for vaporization. So in red, no, let me use purple. Liquid vapor transition. So here we have liquid to vapor, we'll call that gas. Delta H should be positive. So that is this, the H vape. And we'll use the boiling. And we're solving for the delta S of vaporization. So delta G is 0 because, again, they're asking for the delta S of vaporization, and we know that at the boiling point, it's the liquid and gas are at equilibrium. So delta G is 0. Equals delta H, where are we? Vaporization, 59.0 minus the boiling point, 630.15 times, maybe I'll put parentheses here actually. Did I do that right? The math? Yeah, I did that right. Times delta S of vaporization. So if I bring this over, I will have negative. Do you notice how if I go slow enough and I'm pretty confident, I'm not writing negative 59 equals negative blah blah blah. I could do that directly on the calculator in my head, the steps that I've already taken. So I brought that over to make it negative 59 on the left. And then what I would have to do is I would have to divide by negative 630.15. And it's kind of close to this number. So delta S vape equals 0.936 kilojoules per mole dot K. Those are your two answers. I did mention that this is a similar problem is in your practice. Actually, in the last 2 minutes, let us take a look at the practice problems for class 3. Okay, here are the class 3 practice problems. Pretty straightforward. They're asking for signs for the first two. Here we have ice at 0 degrees, water at 0 degrees. See, that's the melting point. So melting and freezing are at equilibrium. Delta G equals 0. Here we have, again, to predict the signs, qualitatively predict whether it's spontaneous or not. Here we have a particle diagram, a cartoon. Here we have equation, again, talking about spontaneity. Let's see, here it is. Heat of fusion, heat of vaporization, and they give you the melting point and boiling point. And they are asking again for the entropy. Okay, so indirectly, they're not telling you that you should use delta G equals 0, but you know to use delta G equals 0 because that is the point where these processes are neither spontaneous or non-spontaneous. They're at equilibrium, either melting or evaporating. Okay, good luck. Don't forget Phoebe's ACE sessions and my office hours if you need any help. And I'll get you class 4 material as soon as possible. But for now, focus on class 1 and class 2 and this class 3.